Okay, so let's look at these, what we call transformation rules. The first one is f of x plus h. Let me give you a few examples of what that looks like. We've just done the absolute value function. So instead of just being the absolute value of x, then this would be something like the absolute value of x plus 2. Okay? Or another common function they're going to ask you about is the quadratic function. So x plus 2 squared is another example of f of x plus h. So it's taking your function, f of x, and it's adding a number to the x part of it. Okay, so inside the absolute value, inside the squared. Okay, let's see here. If we've got e to the x, okay, our exponential function, then that would be like e to the x plus 2. Okay, it's in the exponent. It's right beside the x. What that's going to do is it's going to shift our function left h units. It's going to shift us left h units is what's going to happen there. If we have f of x minus h, so for example, the absolute value of x minus 4 or x minus 1 squared, okay, that's going to move your function right h units. Okay, that when it's with the x inside the function, as I like to call it, it moves at the opposite of what we would expect, right? Plus, we usually positives, we think right and up. Negatives, minus, we think left and down, but in this case, it's the opposite of what we expect it to be. So I'm not entirely sure how they would ask you a question like this, but let me show you what I'm talking about. I'm comparing it to what we call the parent function. Go ahead. So if you're trying to answer a question like this, and if it's asking you, what kind of transformation has been applied, or what does this do to the function, you're comparing it to the original, to that base function of just the absolute value of x. So I would graph both of them in my calculator, and I would see what would happen. Okay, it looks like the exact same function. I'm just over 4 units, over to the right 4 units compared to that regular function. Okay, so if you kind of forget these concepts, that's kind of what you need to do to be able to compare them. Okay, so the next line here is slightly different. Okay, the difference between the first line and the second line is where that number is being added. Is it being added to the x? Or in this case, it's being added to the entire function. So instead of the absolute value of x plus 2, we're talking about the absolute value of x plus 2. Or instead of x plus 2 squared, we're talking about x squared plus 2. Okay, see the difference between those functions where the plus 2 is? One of them, it's inside the function, inside the absolute value. One of them, it's outside of the function, outside of the absolute value. Or inside the squared versus outside the squared. This is going to move it up k units. There's no difference between h and k. They just use something different so that there's a difference between the horizontal and the vertical changes. Okay. Similarly, the minus k is going to move it down k units. So while I've got this in my calculator, let me just add this one to it. If I change that to the absolute value of x and I close the parentheses, minus 4, okay, see how these are all different. This is the parent, the original one, absolute value of x. This one, the minus 4 is inside the absolute value. This one, the minus 4 is outside the absolute value. Okay, so we can compare it there. We've moved that original one down 4 units compared to that original. Okay, all right. The next two are talking about stretches and shrinks. Okay, a times f of x. So we're multiplying the entire function by a constant. So for example, this one says when the absolute value of a is greater than 1. So let's say, for example, this is 3 times the absolute value of x. That is a vertical stretch. You're multiplying everything by 3. So all of your y values are going to be 3 times as tall as they were before. The next one looks exactly the same, a times f of x, but it says when the absolute value of a is less than 1. So for example, let's say 1/2 x squared. Okay, 1/2 x squared. Dakota, put your phone away. 1/2 of x squared. That's taking all of your y values and it's multiplying them by 1/2. That is a vertical shrink. It's making all of your values half as big as they were before. So those kind of make sense. And again, you could see that on your graph. You could look at the table and compare those things. Let me actually do that so you can see what I'm talking about. And to show you how you can figure this out on the test. Okay, let's change this to 3 times the absolute value of x. Get that one out of the way. Okay, so there's the original. There's 3 times the absolute value of x. You can see that it's skinnier. I would go to the table. Okay, look and see how all these y values are 3 times as big as they were before. Okay, y2, all those y values are 3 times as big as before. So you're stretching, you're making those y values greater. Okay, you're stretching it out. And then the last one here, negative f of x, when there's a negative in front of the function. So for example, negative absolute value of x, negative x squared, negative e to the x, negative 3 to the x. Okay, that's going to flip all your functions over the x-axis. Okay, they're probably going to use the word reflect. Because what's happening here, it's just like the ones we just talked about, but instead of multiplying it by a number, it's multiplying it by a negative. So it's taking all your y values and it's changing their signs. Okay, it's taking all your y values and it's changing their signs. So instead of being the absolute value of x, we've got the negative absolute value of x. And that's what those two look like. So it just takes the entire function and it flips it over the x-axis. And like I said, they're going to use the word reflect. Okay, it reflects over the x-axis. Okay, so let's look at your blue sheet now. Okay, we're going to talk about, we've talked about a lot of this stuff before, but I just want to summarize it for all the functions and adding the absolute value function here, and then also add in that idea of what's going on. Okay, so the very first one, f of x is equal to negative 3x plus 5. What type of function is that? What do we call that? A linear function. Okay, we need to be familiar with the names of them as well. Okay, this is a linear function. Let's talk really quickly about graphing it. We can do this by hand very easily. The y-intercept is 5. Okay, so 2, 4, 5. The slope is negative 3, so I go down 3, right 1. Down 3, right 1. Over and over and over again. I can also go up 3 and left 1. Okay, so there is our line. Yes, of course, we could have used our calculator, but I just wanted to review that idea that we can graph that very easily by hand. The parent function, the base The very most basic linear function that we can talk about is just y equals x. Okay, y equals x. The domain of this, all real numbers. Even though it's a linear function, technically linear functions are considered polynomial functions, and all polynomials have a domain of all real numbers. How about the range? Are there any y values that we won't hit? No. Look, whenever you have a function like this and you got an arrow at the very bottom and you got an arrow at the very top, that's going to be all real numbers. You hit everything. If you start at the bottom and go all the way up, you're never going to have a gap or a missing place in the graph there. So that range is all real numbers. How about the number of roots? What is that asking about? What are roots? What's another word for roots? Zeros. Roots, zeros, x-intercepts, solutions. All those words mean the same thing. Okay, roots, zeros, x-intercepts, solutions. So how many roots do we have for this function? How many times does it cross the x-axis? 1. It's not asking what they are, it's just asking how many does it have. It crosses once, and that is it. Alrighty, let's talk about this end behavior. I'm telling you, you're gonna see a question like this. So let's do ourselves a favor, and let's label on this side, we've got positive infinity. On this side, we've got negative infinity. So the first one says, as x goes to positive infinity, as we're going this way, where are y values going? Down. They're going down to negative infinity. Okay? As x approaches negative infinity, as we're going this way to the left, where are y values going? Positive infinity. Okay? Positive infinity. Okay, now these last two, increasing interval, decreasing interval, we haven't talked as much about, so I'm going to try and take this slow with you. When you're trying to figure out increasing and decreasing, you're always going to move left to right. Okay, we're always going to start on the left and we're moving to the right. So when we start on the far left side of our graph, and we go to the right side, what are our y values doing? They are decreasing. This is a decreasing function everywhere. It's always decreasing. So this is decreasing from negative infinity to positive infinity. And it is never increasing. So put none on the increasing interval. Okay? We always go left to right, and the question is, what are the y values doing? Alrighty. Let's keep going. Let's do this with an absolute value function. Now, before we do all that stuff there on the right, I want to talk for a second about the transformations. Since we just made that chart, let's talk about the transformations. What is that -1 inside the absolute value going to do to our parent function, y equals the absolute value of x? Okay, it's the opposite of what we expected to be. So it's going to move us right 1 unit. And what's that -4 going to do? Look at your chart. It's right there. What's the -4 outside the absolute value do? Down. Down 4 units. So really, I don't need my calculator. Okay? I don't need my calculator to graph this. If normally the absolute value function starts at the origin. The vertex is at the origin. I have moved it right 1 unit and down 4 units. So now my vertex is at the point 1, -4. I'm not multiplying it by anything. So remember, I think we talked about this a little bit. The slope of the right side is +1, and the slope of the left side is -1. Now, I'm not saying you can't use your calculator to graph these. I'm just pointing out the fact that after we know this about these transformations, it should be very easy to not have to use our calculator. Okay, so that's our graph. Anybody remember what the domain of an absolute value function is? All real numbers. We can take the absolute value of any number we want to. You can take the absolute value of any number you want to. So the domain is all real numbers. Okay, range. Question we should ask ourselves is, does this graph have a minimum or a maximum? Does it have a minimum point or a maximum point? Yeah, it has a minimum. Okay, it has a minimum. So that means our range is not all real numbers. Okay, the range is not all real numbers. So what is that minimum point right there? What did we say this vertex was? 1, -4. So our range, yes, Gabe, greater than or equal to -4. Our y values are at least as big as -4 at all times. We get everything else that's bigger than that. It's going to keep increasing. Okay, how many roots does this one have? How many times does it cross the x-axis? Twice. Okay, it crosses the x-axis twice. Over here and over here. Now, absolute value functions, do they always have to have 2? What else could happen? How many roots could we have for an absolute value function? We could have 1. It could just touch the x-axis. That vertex could be on the x-axis. Is there another possibility? None. It doesn't have to cross. It could be completely above the x-axis. What if we just shifted it up 1 unit? Okay? What if we just shifted up the function 1 unit? Then it would never cross the x-axis. Okay. All right, so let's keep going. In behavior, on the right side, as x approaches positive infinity, on the right side, where are our y values going? Positive infinity. They are going up. Look at that arrow over there. Okay, they are going up. On the left side, okay, negative infinity. On the left side, where are our y values going? They're going up. Okay, still going to positive infinity. Okay, now, this one's a little bit different from the last one, isn't it? When we get to the increasing and decreasing part, is it always one or the other? If we start on the left side, what's happening first? We're decreasing. Then we get right here, and it starts increasing. Okay, so it's decreasing first. So we start with negative infinity. Okay, we're going left to right. So we start over here until we get to the vertex right here. We are decreasing. Where is the vertex? +1. We use the x value part. Okay, we use the x value part here. Okay, we don't care about the y. We're talking about what the y values are doing. So we use the x values to tell us where it's at. And then it's increasing from 1 all the way to the right, all the way to positive infinity. Okay. I know this is not the most thrilling lesson ever, but this is very simple stuff that they're going to ask you about that y'all can get right. Okay, if you just pay attention to what we're talking about right here. Okay. All right, let's look at number 3. Let's look at quadratic. Okay, it's been a long time since we've talked about quadratics. This one, the parent function would be y equals x squared. Okay, y equals x squared is our parent function. That's the basic, most simple function we can talk about here. Okay, so we're kind of comparing it to x squared if they were asking us to compare. All right, quadratic function. What's its domain? All real numbers. It's a polynomial. Okay, so I'm going to write this under, I'm going to write quadratic, and I'm also going to write polynomial under it. Okay, quadratics are just a specific type of polynomials. But polynomials, remember what that means. Poly means many, nomial means terms. So it's got 3 terms, that's several. Okay? All right. We haven't graphed it yet. I wanted to talk about that stuff before we got into the graph. So let's look at the graph now so that we can talk about the range. Negative x squared plus 8x minus 11. Okay, let's look at the graph. All right, let's go to the table so we can get some specific points to plot here. Ooh, those are way off the charts here. 1, negative 4. That's interesting. That was the same point we had there on the absolute value that we just graphed. 2, 1, 3, 4, 4, 5, 5, 4. We see some symmetry here. Hopefully we do. 6, 1, 7, negative 4. I think that's enough to graph our parabola. Now, this point right here, this 4, 5, is my maximum. It is my vertex. I know that because I see the symmetry in the table. Okay? When I get to this point and the 2 points beside it have the same y value, that means that's got to be the vertex. Okay? That's got to be the vertex. But we can always make sure, go to the graph, is that a maximum or a minimum? It's a maximum because it's the highest point that we can hit there. I can calculate it. Oop, wrong way. I need to go this way. Maximum. Okay, it is 4, 5. Now, I like that the calculator did this to bring up a good point. When you see that many zeros after the decimal, it's just 4. Okay, if you see that many zeros after the decimal place, it is just consider it the whole number. Okay, 4, 5. Sometimes the calculator, it estimates these things. It uses a method of approximating, and that's why sometimes it doesn't just come out and give you the exact whole number answer. But it is 4, 5 for the vertex. Okay, so what did I need all that for? To find the range. Okay, so what is our range here? Is it going to be less than or greater than? Less than. Is it going to be equal to? Yeah. Yeah. Less than or equal to what? 5. Okay. Because 5 is the maximum y value that we can hit. Okay. How many roots does this one have? 2. Let's talk about the same thing we just talked about with the absolute value function. Does a quadratic always have 2 roots? Nope. You can have 1 and you can have none. It's just like the absolute value function. You can touch the x-axis or you can not touch it at all based on where that function is. Alrighty. Let's look at that in behavior. Okay, the right side is positive infinity. The left side is negative infinity. Let's look at where our y values are going. On the right side, as x approaches positive infinity, where are the y values headed? Way down there. Negative infinity. Both of them are. The left side does it too. Okay, the left side also goes to negative infinity. Both ends there are going to negative infinity. Okay, so as we move left to right, what's the function doing first? Increasing, okay? Do that. You just take your finger, okay? Start on the far left side of the graph, and you trace it. Where are we doing? We're going up. We're increasing, okay? Until we get to our vertex there. So until we get to 4, so from negative infinity to 4, we are increasing. Then when we get up there, we start decreasing. And we never change direction again. So it's from 4 to infinity. Okay. Now, I know that gets a little confusing because we're going down to negative infinity and we're using the x values to tell us where this is happening. Okay? We're using the x values to tell us where it is. So we're moving left to right. So from negative infinity to positive infinity. Okay. Let's look at number 4, another absolute value function. Let's talk about the transformations on this one first. Okay, we'll talk about the transformations first. The negative absolute value of x plus 6. Okay, what is the negative in front of the absolute value? What's the negative in front of the absolute value do? Do what? Makes it opposite, okay? It reflects across the x-axis. You've got to know that term. I promise you guys, they're going to ask you a question about that. That's why I'm telling you, it's easy. It is so easy. You just got to right now, I'm just asking you to look at your table, okay? It reflects across the x-axis. What does the plus 6 do? Up 6. Okay, so let's type it in just to make sure that we get everything in the right place. Okay, make sure you close the parentheses after the x because the plus 6 is not inside the absolute value. Okay, so what's going to happen is it reflects it first and then it moves it up 6. So it flips it over and then they go up 6. So 2, 4, 6. Here's what we're looking at. Again, you can use your table, okay, to make sure that you've got the exact right stuff. Okay, my lines aren't so straight, but you get the idea. Okay, parent function, again, is just y equals the absolute value of x. It's just the basic function. The domain of absolute value is always all real numbers. Okay, tell me about this range. Is it less than or greater than? Less than or equal to. Okay, this point up here, this vertex, is 0, 6. How do I know that? Because I started at 0, 0. I flipped it over. I was still at 0, 0. And then I went up 6. So 0, 6 is our vertex. So our range is y is less than or equal to 6. This one still has 2 roots. Let's talk about the end behavior. This one's different from the last absolute value function that we did. The last one that we did was opening up, so both of them are going to positive infinity. On this one, it's opening down, so both of them are going to negative infinity. Okay, take your finger, put it on the far left side of your graph. Trace the graph. What's happening first, increasing or decreasing? Increasing. Okay, it is increasing first. Negative infinity until we get to 0. And then at 0, it turns and it begins decreasing all the way to the far right side of our function, positive infinity. Okay, I have done enough